Today we're going to be talking about how to find the volume of the parallelepiped, assuming that we've been given 3 adjacent edges of the geometric figure. Now, if you're not familiar with a parallelepiped figure, it's basically the 3-dimensional version of a parallelogram in the same way that a cube is the 3-dimensional version of a square. In this particular problem, we've been given 4 points in 3-dimensional coordinate space, point P, Q, R, and S. We've been told that PQ, the line segment from P to Q, that PR and PS are 3 adjacent edges of our figure. What that means is that they all 3 start at the same corner of the figure and go in different directions. And that's very convenient because what that does is it defines for us, essentially, the length, width, and height of our parallelepiped figure. So what we can say here is that if we have some parallelepiped figure like this, we have a vector here, a vector here, and a third vector going out this way, something like that. We've been told that this point where they all connect is P, and then this can be, for example, Q, R, and S, and this is not accurate given the points that we have, but we can think about it this way. If we fill in the other lines of this figure, like so, then you can see how this is a parallelepiped figure where we have 6 parallelograms for the sides of this 3-dimensional figure. If we can model the line segments PQ, PR, and PS as vectors, then we can use the scalar triple product to find the volume of the parallelepiped. And of course, the way that we can model them as vectors, if we want to find, for example, the vector PQ, so we'll say the vector PQ, we just take this point here, Q, and subtract each of the corresponding components from the point P. So what we mean by that is that our new vector, PQ, is going to be equal to, we take the x component from Q, which is 2, and then we subtract the x component from P, so minus a negative 2. Then we take the y component from Q, which is 3, and subtract the y component from P, which is 1, the z component minus the z component, 2 minus 0. And when we simplify here, we see that the vector PQ can be defined by our direction numbers or by the components. 2 minus negative 2 is 2 plus 2, which is 4, and then we have 2 and 2. So the vector PQ is 4, 2, 2. We want to do the same thing with PR and then PS. So the vector PR is going to look like this. We'll take our components from R and subtract the components from P. So we get 1 minus a negative 2, comma 4 minus 1, comma negative 1 minus 0. And when we simplify, we get the vector PR being equal to 3, 3, and negative 1. To find PS, we'll do the vector PS. We're going to subtract our P components from our S components, so we're going to get 3 minus a negative 2, 6 minus 1, and 1 minus 0. And when we simplify, we'll see that the vector PS is going to be equal to 3 minus a negative 2 is 3 plus 2, or 5, 5, and 1. Now we have 3 vectors that define 3 sides of our parallelepiped. We can use those 3 vectors in our scalar triple product to find volume. Our scalar triple product, what we're going to do is take a cross product of 2 of our vectors and then a dot product of our third vector with the result of the cross product. Here's what that looks like. Our scalar triple product will be the vector PQ, the dot product of the vector PQ with the cross product of PR and PS. So if we unpack this, what we're going to do is take the cross product of PR and PS and then the dot product of PQ and our result. If we set up our cross product of PR and PS, we'll say PR times PS, the cross product is going to be the matrix here. We put I, J, and K in the first row always. Then our vector PR, which we already found to be 3, 3, negative 1, so 3, 3, negative 1, and then our vector PS, which we know is 5, 5, positive 1. If we break this out into our discriminant parts here, what we're going to get is the matrix 3, 5, negative 1, 1, so 3, 5, negative 1, 1, multiplied by I. Remember, we take everything that is not in I's row or column, that's this square here of 3, negative 1, 5, 1. Then we're going to subtract the same thing for j. Everything that's not in j's column here is 3, 5, and then negative 1, positive 1. So 3, 5, negative 1, positive 1 times j. And then we add whatever is the same thing for k. That's 3, 3, and 5, 5, the things that are not in k's column. So 3, 3, 5, 5 times k. Now, at this point, remember that we multiply the upper left-hand corner with the bottom right-hand corner, so 3 times 1 is 3, and then subtract the product of the lower left and upper right-hand corners, so 5 times negative 1 is negative 5, so we get 3 minus negative 5 multiplied by I, minus 3 times 1 is 3, minus 5 times negative 1 is negative 5 times j, and then plus 3 times 5 is 15, minus 3 times 5 is 15, k, and when we simplify further, you can see that we'll get 8i minus 8j plus 0k, so we can just call this 8i minus 8j, which is the same thing, if we do this vector representation the other way, as 8, negative 8, 0. So that's the vector representation of the cross product of PR and PS, 8, negative 8, 0. Now, if we want to find the dot product of PQ and our result, we'll just say PQ, and the dot product of PQ and our result here, which was the cross product, is going to be equal to, remember to take a dot product, we multiply these inner components of our two vectors. So what we're going to do is take the x component 4 and multiply it by the x component over here, 8, so we're going to get 4 times 8. Then we're going to add to that the product of our y components, so 2 and negative 8, 2 and negative 8, and then add to that the product of our z components, 2 and 0, so 2 times 0. When we simplify, you can see that we'll get 32 minus 16 plus 0, which is just going to give us 16. And remember that 16 is the volume of the parallelepiped defined by these 4 points P, Q, R, and S when PQ, PR, and PS are 3 adjacent edges, 3 edges that touch at a corner here of our 3-dimensional parallelepiped figure. One thing to remember also is that if you get a 0 result, if you get a result here of 0 of the scalar triple product, you find that the scalar triple product is equal to 0, that means the volume is equal to 0, which means that we don't have a 3-dimensional figure, we have a 2-dimensional figure that has no volume. What that means is that, for example, this point here, R, that kind of defines the height of this parallelepiped, is actually in the same plane as P, Q, and S, which brings this volume down to 0. If all of these points are in the same plane, then we can say that the 4 points are coplanar. So if you have a volume of 0 here as a result of this scalar triple product, one thing you can conclude is that these 4 points lie in the same plane, and we can call them coplanar.